engineers, and our website is alpinenow.com. Let me go ahead and introduce our first speaker. So we have two speakers today. So his name is Chris Berner, and he is a software engineer at Facebook, and he is going to be talking about machine learning in Presto.
All right, let's see, is this on? Sounds like it is. So my name is Christopher Berner. I'm a software engineer at Facebook, and I work on the Presto team. Presto, for those of you that don't know about it, is a distributed SQL query engine. And as a hackathon project, I added machine learning capabilities to it. And basically the idea of the project was to marry the power of machine learning to the simplicity of SQL to allow more people to do machine learning. I previously worked on the newsfeed ranking team, and so I did a lot of machine learning work at Facebook. But what I found is that a lot of other teams don't necessarily have machine learning people or even that many engineers, but they still want to do modeling. And so SQL seemed like a natural way for them to do that. So my talk's broken down into a couple pieces. First, I'm just going to go over what Presto is for those of you that aren't familiar with it. And then I'll talk a bit about why I think machine learning in SQL makes sense. Then we'll have a demo, which will be live, and hopefully will go flawlessly. And then I'll go over some details of how Presto ML actually works, the architecture of Presto more generally, and then finally talk about some future work that I hope to see done on Presto ML. All right, so what is Presto? Like I said, it's a distributed SQL query engine. And what that means is that it's basically like MySQL or Postgres, except that it runs on hundreds or thousands of servers. It also is only the compute and query side of Postgres, meaning it doesn't actually do any data storage. It only processes queries. And so to get the data, it has a connector API, which is a few thousand lines of Java code that you write typically to connect it to whatever data store you have. And so we ship with a number of connectors. There's a connector for HDFS if you have Hive data. There's a connector for MySQL, Postgres, other JDBC databases, Cassandra, Kafka. I think there's some others that I missed too. And it was originally designed for low latency interactive analysis. Facebook open sourced Hive, must be like 5 or 6 years ago now. Which was basically SQL. It's not quite SQL, it's HiveQL on top of Hadoop. And that was great, but it tends to be fairly high latency. That when you submit a job, because it has to convert it into a MapReduce pipeline, there's just a lot of overhead in doing that. So Presto was designed from the ground up to be low latency and for interactive analysis. It's also ANSI SQL, not HiveQL. And it has a connector system, like I mentioned, which has allowed us to use it for a lot of other products. It started out originally just being used in our data warehouse, but now we're using it for some user-facing reporting products, not for normal Facebook users, but for advertisers. And we're looking at using it for a bunch of other use cases as well. All right, so why machine learning in SQL? Every time I've written a machine learning pipeline, it goes something like this. You have a bunch of data that's in databases, frequently not just one database, but a couple databases, also maybe some other proprietary data stores that you've built. And the first step is collecting all of the data in one place so that you can extract features and build a model. This, of course, involves first connecting to all of your different sources, getting the data. You probably end up dumping it in a variety of formats and have to deal with normalizing your JSON data, your comma-separated values, deal with character encodings and UTF-8, which is something I always love to do. Then, finally, you get all the data into the right format, you extract your features, and then you start writing a C++ binary, or maybe Python or Java. But I've used C++ most frequently. And at that point, things go pretty quickly because I know how machine learning works. And so I write a binary that reads in all the features and trains the model and makes some predictions. And then I have to put it into production. And that's a whole nother bunch of work. But really, it would be nice if I could just do all the experimentation by writing a SQL query. And with Presto, you can do that. Presto, like I said, has connector APIs, so it's already connected to all the data stores that I want to get data from. And so in this example, we're training a model to learn whether emails are spam. So you just write a SQL query, create a table, as select learn classifier. So this is where Presto ML comes in. Presto ML is a plugin that adds new types and new functions. And one of those functions is the learn classifier function. And then you can just say from emails in your query. And it will read all the data from the emails table, build a model, and then store it back in your database. Yeah, so all the training is done in SQL. And then saving the model, you can just write it back to your data store because Presto has this connector interface. You can write it back to the same data store that you got your data from. You can even write it to a different data store. And this, I think, is really great because I don't know about the rest of you, but I've frequently done some sort of model prototyping where I've built a model on my laptop, and then 6 months later, I've given the predictions to someone, and they come back, and they're like, oh, hey, do you still have that model? Can we run it on some new data that we got? I'm like, oh, yeah, I deleted that, but we can try to rebuild it. So if I can just save it into a distributed database, that's great, because it's never going to go away, and these models tend not to be very big. You know, maybe they're 10 megabytes, 100 megabytes, and so they're not going to take up much space on our distributed data stores, whereas they would on my laptop, which is why I tend to delete them. The other great thing about SQL is, like I mentioned, a lot of teams don't have machine learning experts. They do, however, have analysts and business people that know how to write SQL. And at least in my experience, the analysts I've worked with are all very smart people that understand statistics and understand the data really well. They just don't necessarily know how to write C++ code and do machine learning. And so they're totally capable of finding tables that have useful features in them, doing some feature extraction, and putting those into a SQL query, which was sort of where I got the idea for building this. All right, so let's do a demo. This will be a live demo, so I hope it goes smoothly. All right. So I've loaded the Fisher Iris dataset into Postgres. And this first query that I'm going to run is just creating a view of that table in Presto that has an extra column for indicating whether or not the data has been selected as a training row. So, whoops. All right, so here I've got the Presto shell open. I'm just going to paste in the query, run it. Says that it created the view. And then the next thing we're going to do is create another view of hyperparameters. So a great thing about Presto is that because it's a distributed compute engine, we've got tons of compute. And so selecting hyperparameters is pretty easy, because if you want to try out 100 or 1,000 different combinations of parameters, no problem. Just submit a query and you get 100 machines to all build machine learning models for you, and then you can figure out which one's the best. All right, so now we're going to create another view that has the actual models in it. So this does a join between the iris data and the hyperparameters table that we created. And then it does a group by parameters. So that's a group by each of the sets of hyperparameters. And then for each set of hyperparameters, we train one model, which is this function here, learn libsvm classifier, that just takes the class, the features, and the parameters you want to use. All right, so we're going to do that. Cool. All right, so now we're going to make some predictions. So I have this where clause in my query, where not training, so we're going to select the non-training data. And then we're going to use one particular set of parameters, just the linear kernel. And to make the prediction, you just call this classify function. And it works pretty much how you would expect. You just give it the features, and you give it the model that you want to use, and it makes a prediction. So we're going to select the true class from the data, and then the predicted class. All right, so we can see the model did pretty well. They made one mistake. The true class was Iris virginica, and it predicted Iris versicolor. But the rest of them look like they're correct. So that's encouraging. Now we can apply some SQL and get a more summarized report. So this query is very similar to the last one, except we're going to do a group by parameters. So for every set of hyperparameters, we're going to run this function, which is just count if the true class is equal to the predicted class. So for each set of hyperparameters, we'll find out how many correct predictions it made. And we can see that the linear kernel definitely did the best. It got 29 correct, whereas all the rest only got 10. I didn't really spend any time tuning these hyperparameters, so I'm not surprised that the other ones didn't do well. And then this last query uses a sort of convenience function, the evaluate classifier predictions, which basically just creates a report. This is for people that maybe don't know as much about machine learning, and so they'd like something a little bit more detailed. And so it summarizes for every hyperparameter set, the accuracy, the prediction, the precision and recall for each class. And yeah, you can see it keeps going for every kernel that we tried. All right, let's go back to PowerPoint. Okay, so some more details about how Presto ML actually works. Like I mentioned, it's a plugin for Presto. So plugins in Presto can provide new SQL types, new functions, new connectors. That's how it connects to different data stores. And so the ML plugin provides new types. It provides a classifier type, a regressor type. I think it also provides a machine learning features type, and then the functions for training classifiers, making predictions, all those other things that you saw. And then under the covers, the way that it works is it just takes the data that Presto feeds into those custom functions, converts it into the in-memory data structures that libsvm uses, and then calls into libsvm. And right now it just supports regression and classification, but it would be easy to extend it to support other things and other models besides SVMs. All right, so now I'm going to talk a little bit more about the architecture of Presto more generally. So I'm going to walk through planning a query and then a little bit about how Presto would execute that query. So this is pretty similar to the one I showed earlier. We're training some spam models, but this time we've decided to train one for every user. So we just have a group by user, and then we include that in our select clause. So the first step of planning a query is building the logical plan. And for those of you that have spent much time trying to optimize Postgres or MySQL queries, you're probably sort of familiar with query plans. You start out with something like a table scan. In this case, we're scanning the emails table. Then the second operation that we do is the grouped aggregation. And it's grouped because we're grouping by user ID. So for every user, we're going to apply this learn classifier function. And then finally, we have the create table, just to save the results out. Now in Presto, because it's a distributed SQL query engine, we then have to convert the logical plan into a distributed plan that can run on all the worker machines. And so in a lot of cases, it translates one-to-one. The table scan gets converted into a distributed table scan. But then you have to perform the shuffle operation, because the second step is going to be the grouped aggregation on user ID, and so you need to get all of the rows for a particular user onto the same machine so that you can apply that grouped aggregation. And so there's the shuffle step in the middle, and then the second stage is the aggregation and the table writer. So we process each grouped aggregation, write it out to a table, and then at the end there's a single machine that processes the table commit, just to make it atomic. Presto also has a lot of distributed optimizers, and so it can take advantage of things like the physical layout of your data. And so if your data store happened to be sharded on user ID, and the connector communicated that to the Presto query optimizer, then the query optimizer could actually merge these bottom two stages. And so you would not have the shuffle in between, because the data is already sharded on user ID, it would know that, and then it would merge them together so that the table scan, the aggregation, and the writing would all be done in a single stage without any network traffic. So we've made a number of optimizations in Presto to make it low latency. Like I mentioned at the beginning, the design goal was low latency for interactive queries, because Hive is great, but the latency tends to be high. And so one of the first trade-offs we made was everything is done in memory. In Hive and MapReduce more generally, you process a map step followed by a reduce step, and in between, you checkpoint your data to disk. Presto doesn't do any of that. There's no fault tolerance. Everything is kept in memory, and if a machine goes down, you just have to resubmit your query, which, again, is kind of fine because the design goal is for interactive queries, so if your query fails, you're just going to resubmit it. We also find that in general, because queries tend to only run for a few minutes or tens of minutes, you normally don't have machines crashing in that time span. We do plan to add fault tolerance in the future. We could have some sort of in-memory checkpointing, but that just hasn't been a priority at the moment. The other ways that we optimize for latency is that Presto is not a generalized compute engine. It's very specialized for processing SQL queries, and so it has a lot of specialized operators just for processing parts of SQL queries. And then we schedule adaptively so that if you have a worker that's straggling, we don't give it more work. We'll give the work to machines that are running faster. And that's, again, to reduce latency in your query. So all of this makes the Presto execution model probably more like Spark rather than like Hadoop. Everything is done in memory, and it's done as a pipelined DAG. So rather than waiting for all of your mappers to finish before you start your reducers and then your next step of the query, that previous query plan that I showed you, the table scan and the aggregation might run concurrently. You wouldn't wait for the table scan to finish. Okay, so a little bit more about our connector API. Connectors are pretty simple, or at least they can be simple. Writing a basic connector is probably only 2,000 to 3,000 lines of Java code. I've written several of them to connect to internal data stores at Facebook. And it's basically just 3 APIs. So when a query comes into Presto, it parses and analyzes the query. And as part of that, it uses the metadata API of all the connectors that are loaded. And so at this point, for the Presto ML plugin, it would ask the Presto ML plugin what types and what functions it had loaded, because it needs that to analyze the query. Similarly, for your connectors that connect to a data store, it needs to know what tables exist and what the schema of those tables are. Then we have the planner that I talked about, and then the scheduler. The scheduler uses the data location API, which tells Presto where the data is located physically and how to access it. And this is where we make a lot of the distributed optimizations, like merging those 2 stages of work together. That would be done if you knew that the data was already sharded on user ID. And the data location API also specifies the physical hosts that have data so that Presto can schedule the work closer to the data if it can. And then finally, on the workers, they use the data stream API, which is where they fetch the raw data. And that can either be done processing 1 row at a time, or more commonly it's done processing pages. Presto processes most things as columns of data, and so we'll fetch an entire page that has your 2 or 3 columns, or maybe more than that. And then as far as executing the query, you have a query that comes in from your client to parsing and analysis, and then uses those metadata and data location APIs that I talked about. And then the scheduler schedules stages of workers. And so the first stage of workers in the query that we were looking at earlier would be the table scan. And so that's what you see here of 2 different workers that are using the data stream API to stream data out of your database or out of Hive and HDFS. and then they would shuffle it into a second set of workers, or possibly a single worker. We also make a lot of optimizations in the workers themselves. They primarily use flat data structures, and they also generate bytecode for evaluating SQL expressions. This is, again, just to reduce latency and improve efficiency. And provides a pretty significant speed up, actually. I think when we added the bytecode compiler, it sped up our queries by about 5 to 10x. And it will actually compile functions that are provided from plugins into the bytecode that it generates for an expression. So in those queries that I showed you earlier, where it had the classify function, it would compile that along with the other comparison operators into a single Java method that it would then invoke as it was processing the rows. Yeah, the scheduler is also actually in the middle of being rewritten now. We're rewriting it to reduce latency even further. We've learned a whole lot since we originally wrote it. And so we're now adding in support for better memory management in our clusters. Presto right now does not, or is very naive in the way that it manages memory. Every task, that being these tasks that are running on the workers, has a memory limit, which is configurable, but your entire query has no limit. And so you can imagine that your query could be in multiple stages, and since they all run at the same time as a pipeline, there's really an unbounded amount of memory that your query could use up. And this we see crashes our clusters from time to time. But in the near future, we will manage all of the cluster's memory centrally on the coordinator. I think I forgot to mention that the coordinator over here is a separate machine that doesn't actually do any work. It just coordinates the queries. It handles all of the planning of queries, the scheduling of work, and soon it'll handle the management of resources, that being memory now. But in the future, we'll probably also include CPU time and resource groups so that we don't starve out queries. So in the future work that we hope to do, we would obviously like to add in more models. Like I said, we only support libsvm right now, but it would be pretty easy to support other types of models, as well as completely different workloads like collaborative filtering or clustering. Collaborative filtering would probably be a really useful one because it's something that product people tend to want to do, and they often don't have the experience to do a lot of machine learning on their own. Right now, also, the modeling is all done on a single machine. Since we use libsvm, it just collects all of the data onto a single worker, and that worker builds the model. Therefore, you can't run on really, really large training sets. It has to fit in memory on a single worker. And so distributed training is another thing we'd like to add. It's probably going to require a lot of changes to various parts of Presto to make that work, because right now we don't have support for functions that are processed distributedly but then share data during their execution. And so your learn classifier function has to just run on one machine. Then some other things are automated hyperparameter tuning. So you saw in those queries I had to put in some sort of group by the hyperparameters and then train different models. But I think we could actually introduce either functions or a special grammar in the language that just allowed Presto itself to pick hyperparameters for you and try them out and then tell you what the best settings were. Similarly, feature selection and feature extraction, I think, are really important, especially for non-technical people, because that's not something they're going to have a lot of experience with. Yeah, so I think that's pretty much all I had. Here's my contact information if you have any questions. And I think we have time for a couple questions. Is that right? So yeah, I'll take a couple questions. Yes.
So why did you start it with libsvm?
I started with libsvm mainly because I had used it on my last project, and I was trying to reproduce the same pipeline that I'd built in my previous project. Other than that, no particular reason.
Does it also produce graphs? Like if you do binary classification, do you compare all the binary classifier on a ROCR curve stuff sort of thing?
Oh yeah, can it produce graphs? That's a good question. Presto actually has some very basic plotting functionality that I have not played with very much. So I think you could do that. It might require adding some new functions. But it's certainly possible. It would also be entirely possible to hook up Presto to some other UI that you had that did the plotting, and then do your plotting there. Internally, we have a bunch of tools, both desktop tools and web tools, that talk to Presto via a JDBC driver or via our REST API, and they just fetch the data, and then they do their own plotting. So you can do it that way also.
So I saw the result of the classification. It's like a linear kernel produced the best results. So, but usually when I did my project, usually the RBF kernel produced the best results. So I wonder what kind of method you use to tune the parameter, because there are some parameters in the either polynomial or RBF kernel to tune.
Yeah, so this was just a demo. I didn't actually tune the parameters at all.
Oh, I see.
And so I think it's just because the parameters were probably set completely wrong for the RBF kernel. That would be my guess.
Okay, I see.
Yeah.
Thank you.
Hi, so I have a question not about the machine learning, but about the SQL.
Sure.
Have you done any benchmark testing for performance against, I don't know, Postgres or SQL Server?
Yeah, so not against Postgres and SQL Server specifically, because those are not distributed, and so the comparison would not really be fair. Presto is mainly targeted at analytics workloads, so not transaction processing. But we have compared it against Impala, and we've also compared it against Hive. We found that for Hive, it's typically 5 to 10 times faster. And that Impala, they're pretty close. It depends on the query you're running. Sometimes we're faster, sometimes Impala is faster.
And one more question, do you have a limit on the amount of data?
A limit on the amount of data? Not really. So as long as, so the one limitation that exists is that everything is in memory. So you need to have enough distributed memory in your cluster to hold whatever data you need to process. Now, that doesn't necessarily mean you need to hold the whole table in memory, because it's pipelined execution, and so the data is streaming through. And so if you're just doing something like a count star or a sum, it's going to stream the data through and use up almost no memory because it's just counting or summing. However, if you're doing something like a group by on user ID, and you're at Facebook, where we have more than 1 billion users, you're going to need to hold 1 billion groups in memory. And so that's going to need quite a lot of memory. But generally, we've found that you can process pretty much every query that you could run in Hive in Presto, and the in-memory restriction is not a problem. Yeah, in the front.
Do you have directions on how to get started? Yeah, my question was, do you have any instructions on how to get started with Presto? Can we go to your GitHub and download it and start running it?
For sure, yeah. So there's a website, prestodb.io. Yeah, you can also go to my GitHub. You can see the Presto source code. So we do all of our development on GitHub. We run the latest release from GitHub in our production clusters with no modifications. And so yeah, you can follow along with the development there, but prestodb.io would be the place to go.
So what is the maximum dataset size that you have tested against this one?
The maximum data size that we have tested, I guess, so as far as the largest query that has ever been run in Presto, I think we've run it on like a petabyte of data. I think typically the queries are probably in the like tens to hundreds of terabytes range, are probably the biggest ones that we run regularly. But yeah, I believe we have tested it with queries up to a petabyte, and that range is fine.
What kind of control do you have over, for example, if you want to do mini batch learning or add your own kind of learning algorithms, but use this to help get the data?
Yeah, so what kind of control do you have? So that learn classifier function that I showed you was entirely provided by the plugin. And so the interface for that code is just a Java method. And as I recall, it has 2 or 3 parameters. One of those parameters is just a data structure that's basically a list of rows, and each row is just features. So you can just take that data, transform it into whatever format you want to, and call into whatever library you want to. So in that case, it just converts it into, I think it's arrays of arrays that libsvm uses. Just does that conversion, and then it calls straight into libsvm. So yeah, you could use any modeling technique you wanted.
Okay, maybe one more question.
Is there any particular type of SQL query that you can run that you can't run with Presto?
Any query you can run that you can't run with Presto? Yeah, there's certainly parts of the language that we haven't implemented yet. So Presto was only started about 2 or 2.5 years ago. And so we've been progressively implementing more parts of the SQL standard. The most recent thing we added was the unnest keyword and support for arrays and maps. So yes, things that I know that we don't support are scalar subqueries. I also think that we don't support the exists keyword, and we don't support the intersect keyword. But otherwise, we support most things. You can do insert, delete, drop table. Yeah.
Okay, let's thank our speaker. Thank you. And if there's time at the end, we might have time for a few more questions for Chris. While our second speaker is setting up, let me go ahead and introduce him. So Mohit Singh is a data scientist at RDO. So he is RDO is one of our building neighbors at Alpine. And so he actually gave a talk at Alpine not that long ago, but this is a different talk. And he's going to be speaking about non-parametric Bayesian feature engineering is machine learning.
Muting the mic. Okay, thanks. So hi everyone, my name is Mohit Deep Singh, and I'm working at RDO as a data scientist. So just a quick shout out, we are also hiring. So today I'm going to talk about something, today actually I'm going to talk about a lot of metaphors, a lot of them, so bear with me. And in particular, I'm going to talk about this something called as Chinese restaurant process, which is kind of like a non-parametric Bayesian method. And then here is the outline of the talk. Like I'm going to give a general introduction of and give a motivating, build up a motivation to Chinese restaurant process, and then like from there take all the way up to like if time permits, all the way up to Chinese restaurant franchise, which is another metaphor. And I also have a demo to like kind of show that all these things which we are talking about, they actually work and give qualitative results. All right, so one of the fundamental philosophies in big data is like you store a lot of data before without thinking how you are going to use the data, right? Like just like we heard in Chris talk, like you can store a lot of data and then later you are thinking about what are the use cases of your data. And one of the fundamental questions which keep coming back to you is like when you are starting something, how do you get started? Where do you start? And fortunately, unsupervised learning techniques kind of helps you in exploring and understanding the structure of your data. But in this particular talk, I'm going to talk about like what are some of the fundamental issues in the popular unsupervised learning techniques and like how non-parametric Bayesians can kind of like help in dealing with those issues. And so mostly in machine learning, you have two kind of problems, right? Like unsupervised learning and supervised learning. So if you know the right answer, you get supervised learning, and otherwise you have, if your data is unlabelled, which is like pretty much like I think the theme of this talk, then you have unsupervised learning. But in both the cases, what essentially you are doing is computing likelihood estimation, or you are computing some MAP estimation. So if you are from the stats background, you might have read that, there are some properties which make an estimator desirable, and like maximum likelihood estimator happens to be consistent, they are asymptotic, and like they are very efficient, and you thought, okay, ML is a good estimator. And like if you are from stats background, there are a lot of other estimators, but these have, under certain conditions, these have some guarantees that these will perform very well. And same is kind of true in unsupervised learning as well. You are essentially computing likelihood estimate, but since you don't know the right answer, you kind of introduce this latent factor or latent parameter, and then like since that's very hard to optimize, you rely on expectation maximization techniques. So that's like at the core, that's what we are doing in both approaches. And the central theme at the very core of all this problem statement is data. And two of the fields which has emerged from this central theme from data is computer science and statistics. So computer science usually deals with managing, how do you manage your data, how do you efficiently query your data, or there's areas like algorithm data structures, whereas statistics helps you to reason about uncertainty in your data. So how reliable is how much you can trust your data sources to be, how reliable your predictions are. And machine learning kind of draws inspiration from both these two fields. And today we are going to focus on the statistics parts. I think the first talk was mostly on the computer science, but let's talk about some statistics in this talk. And if you are outside the statistics field, like you might have heard about Bayesian versus Frequentist, but like if you are working in this field, this is something which comes again and again, and like you kind of wonder what this all debate all about. And we are not going to solve that debate today. I guess like it's going on for quite some time, but like who are the Bayesians and who are the Frequentists? So essentially, you have a risk function, you have a loss function, right? Like this L, which is a function of your parameter of your model and your data X. And so what Frequentists tend to do is like they try to compute the average over the sample. So try to capture the fluctuations in your data, right? And so that's like what Frequentists do. And Bayesians, like they like to fix the data set. So they're like, I don't want to look into any other data set. Whatever data I have got, that's it. And then once they have, so you condition on this X, right? So based on whatever I have seen, you condition on X, that's fixed. And then you try to get rid of the parameter by introducing the priors, right? So in Frequentist domain, your parameter is the fixed and your data is the variable, whereas in Bayesian world, your data is fixed and you represent the uncertainty in your data by this random variable, the theta. And if by now it's not clear, today we are going to be Bayesians actually, so I apologize to my Frequentist friends over here. Another dimension to add into this current picture is parametric and non-parametric. So what are parametric models? So actually most of the models we know about, which we are using, are actually parametric. So these are models which have, well, parameters, right? So linear regression, logistic regression is a good example of that. So if in your model with fixed number of parameters and it doesn't grow with your data set, that's parametric models. Non-parametric models are the models which are not parametric models, but like, what exactly does this mean? So, and why do we have these, two different school of thoughts? So think about it in frequentist approach, what you are essentially doing is you are fitting parameters to your data. So your learning problem is posed as what are the parameters, what are the best parameters that fits your model well. And if you have a lot of parameters, that's actually bad because you mostly think about overfitting, right? Like, so if I have a lot of parameters, your model tends to overfit, and then you regularize, and which basically shrinks some of the parameters to 0. And then like you kind of say that, okay, the generalization error is good enough. So probably these are good models, and this will kind of predict the future data instances well. But non-parametric Bayesian guys are actually goes into exactly opposite direction. So they tend to think that the world is a very complex place, right? And any data which is coming from this real world is equally complex. So you don't actually need less parameters, but you need more parameters. A question you can ask is like, what about the overfitting and stuff? And the good thing about the non-parametric Bayesian is you don't overfit because you are not actually fitting your data model to your data. And so, because in frequentist approach, what you are doing is you are posing learning as kind of like optimization of the parameters. You are posing it in an optimization way. Whereas in Bayesian world, what you are essentially doing is you are thinking of your problem in terms of inference here. So you have a bunch of parameters. You have a lot of parameters actually. And then when you want to do an inference, you are essentially integrating and summing out those parameters. So I think it's a really good way to sidestep the overfitting issue as well. So all right. So clustering, so it's one of the most fundamental problems in machine learning. And it's actually a very well-researched topic. But here is a sample data set. So like, if I have to ask you like, where exactly are the clusters, then you can kind of like take a look at it and kind of like say, okay, here, these are the regions of the clusters. But even in the simple examples, if I ask you how many clusters are there, so like, there is no right answer to this. So you can say like, some people will say there are like 2 clusters, one this and another one is this, and then some people will say, oh, I see 4 clusters. So even in this simple case where you can eyeball your data set, it's very hard to say where exactly the clusters are, right? And then you have some heuristics like elbow curve, AIC, BIC, or models. You can pose it as a model selection problem. That say, okay, I can kind of like do some hyperparameter tuning and come up with some K which kind of generates the model well. But what happens if in the future you start getting points over here? So should you merge this cluster? So if in future I get more data instances in this particular area, should your belief about number of clusters change? So that's what like the non-parametric approaches are. You want your data to tell how many clusters are there in this particular data set. So LDA, so a good way to think about this latent Dirichlet allocation, which is also called LDA, is it's kind of like the kmeans in Bayesian world. So it's probably the first parametric model. This is not non-parametric model you'll ever see. So let me just briefly go through this. So basically so alpha and beta are the hyperparameters to your model. And then basically what you do is like theta represents your clustering distribution. So if you have if you want to have k clusters, theta will be a k-dimensional vector. And it's essentially a probability distribution in a simplex plane, which means like theta is essentially a Dirichlet distribution. So for each document, what you do is like you sample one of the topics, and then for each document, you sample a topic, and then for each word, you kind of like, given this topic, what is the probability of observing this word? You do it again and again, you get a distribution on your topic, and you do it again and again, you do a distribution over your corpus. And by the way, like, is this notation clear? Like, this is a plate model, which is a way to, represent a graphical model. So what this is essentially a tree. So you can think of it as like, if I have m documents, and each document I have n words. So think of it in that sense, like you have m data instances, and each of them has like n features in that particular instance. So you can like think of it as plates which is stacked on top of each other. So, okay, but this was still a parametric model. And so how do we extend this to non-parametric Bayesian approaches? So a very fundamental equation in Bayesian world is this Bayes theorem, right? Like posterior is directly proportional to prior times likelihood. And if your theta is Euclidean parameter, you basically get that standard notation which we all know about. But if I want to extend it to non-parametric world, if I want to have an infinite dimension vector, so let's introduce some terminology. So if G is a stochastic process, so stochastic process is nothing but a fancy way to say that I have infinite number of random variables. So if that, it's kind of a measure. So if G is a stochastic process, then I can actually write my equation in this way. It's kind of symmetric, but there is some caveat here that even though we can write Bayes equation over here, but you cannot actually compute this analytically. So which is kind of like a weird notion that you can write the Bayes equation, but you cannot actually compute the posterior density because like we are mostly thinking that as long as I can write this formula, we can always draw some distribution of the posterior. And then next couple of slides, it will be clear why we cannot apply this particular Bayes rule in this particular setting. So, all right, so with all this, let me introduce this metaphor Chinese restaurant process. So think about a Chinese restaurant which have infinite number of tables. So the first person comes in and basically decides to sit on the first table. So this happens deterministically because like you have infinite number of tables. You come in and you can sit on any table. You can call it as, okay, here is where I am starting to count my table. This is the table number 1. So now when the second person comes in, you have two options. You can either sit or you can either join the existing, you can either join the person sitting in the existing table, or you can sit in a new table, right? And how do you decide this, like whether I should sit with the person who is already sitting there, or shall I join in a new table? So it's basically based on this rule. You join an existing table based on number of people sitting in that table. So it's kind of like a preferential attachment scheme, which is also like rich gets richer. Before you start this process, you fix some parameter alpha naught, and you basically you either join a new join an existing table with the proportionality ni, or you join an empty table alpha naught. So after n people are sitting, you will get n random partitions or n random clusters. And so even though the number of clusters is random, you can have infinite number of clusters, but in practice, the expectation of how this particular cluster grows with log n. So if you have n customers, you can expect almost log n occupied tables. And then like, how do we extend this metaphor to clustering? So actually your tables represent the clusters and the customers represents the data point. So basically when the first person comes in, he or she draws some parameter vector from a prior distribution, which we'll see in next few slides. And then so the first person comes in and says that, okay, I'm from some Bayes distribution, he'll draw the parameter vector phi1. If it's a Gaussian distribution or if it's a Gaussian mixture model, this phi is nothing but the mean and covariance. And then that particular parameter is fixed with this particular table. Any other person who now joins this particular table inherits those parameters. So your prior comes from G0, the first person drawing that vector. And then likelihood is basically everyone who sits into the existing table will inherit those particular parameters. And then once you have the prior and the likelihood, you can start your Bayesian inference. But like I said, you cannot actually analytically compute it. And there are some techniques called variational inference or like MCMC techniques, which helps you to get an approximate answer. Okay, so before we kind of formalize the Chinese restaurant process into more, let's say, statistical setting, there are a couple of things we have to first go through or know about. Exchangeability. So it's actually, I'm sure all of you have heard about the bag of words model. So it's kind of like the similar, so bag of words model in Frequentist domain works because of the IID assumption, right? But in Bayesian setting, you cannot have the IID assumption, and I can probably give an intuition about that. So if you are in Bayesian world and you have a balanced coin, and you flip that coin 999 times, and all those times you get a heads. Since if you are making an IID assumption, then the 1000 flip, you cannot say that my 1000 flip, it's more likely, even though you know it, that the next flip is probably going to be heads. But since you have made an IID assumption, you cannot actually formally write it that way, because it'll be still half, because my next flip is independent of all the previous flips. So exchangeability more formally means that if I have a sequence of random variables and I randomly shuffle it, the joint probability distribution will be the same. So it's a weaker assumption than IID, but it kind of helps us in developing some Bayesian machinery to solve some of the interesting problems. And to give another metaphor is actually this model called Pauli urn model. So here is basically an example. So imagine you have an urn containing green and red balls. And then basically what you are doing is you are drawing a ball, and you are saying that if you observe, you draw a ball, you look into that ball, and if that happens to be the green, you basically replace A balls of that color back to the urn. And you introduce a random variable X, which is 1 if the draw is, let's say, a green ball. So let's say you observe this sequence of, you observe the X, and these are the random variables you are saying. So basically the first ball is a green ball, so this is the probability of seeing the green ball. Now you have replaced you have added A more green balls into the urn. So now next time again I see a green ball, so now you have G plus A green balls, and then that's the probability distribution, and then basically that's the sequence. So if I randomly shuffle this sequence, so let's say that I shuffle it and 0 is here and 1s are there. So all the change you have to do is basically this red comes here, so R comes over here, and if G goes over there and G plus A goes over there, then essentially you have the same formulation, but you can see how the end result will not change given how I shuffle this particular sequence. So that's essentially what exchangeable means. And then we have another interesting theorem called Affinity theorem, which basically means that if my sequences are exchangeable, given some measure G, I have an IID assumption. So if I have a measure called G, then all my probable likelihood distributions are kind of independent of each other. And then what this theorem also tells us is that there is some underlying distribution G, which we don't know about, which is a latent factor. But if I know that, if the sequence is exchangeable, there exists some underlying prior, which is so you can think of it as likelihood times prior, where G is some stochastic process, which we introduced earlier. But basically, it kind of breaks down this particular notion of how I can, introduce this IID concept and basically sample from the sequence in a parallel fashion rather than thinking of it as a sequential problem. And with all this particular concept, so let's introduce our first, model, which is called as finite mixture model. So I'll kind of go through, and you can read more about it in this particular tutorial from Michael Jordan. So basically, what this particular model means is so both the diagram and the equations are kind of equivalent. So your G is basically a function of pi and delta phi. So delta is indexed by phi, which is, so G naught is some underlying distribution. So what you are doing over here is basically delta represents the location of X. So I have X and Y. So delta basically tells me where exactly in the space these atoms are. So okay, this is also another point that the draw from the Bayes distribution are atoms. And this is one of the reasons you cannot apply Bayes rule, because your G is not some density function. It's actually some discrete lines, which are also called as atoms in this particular field. So what you do is your first process is you're drawing K times from, so here is the K. So you're making K draws from this underlying distribution, and you get these Bayes, the location in the points. And then you have another parameter pi, which is a mixing parameter, which is drawn from a Dirichlet distribution of parameter alpha naught. So what pi does is basically determines the height of your draws. So delta phi tells me where my atoms are, and pi tells me how tall these particular sticks are. And then you basically draw theta, which is also a random variable from G. So basically based on the height, you draw a G, and then simply you fix a Gaussian which is centered around this particular model. So right now you might be thinking about why I am talking about this and what does this has to do with Chinese restaurant process, but in the next few slides again it will be clear that how this we can extend it to the Chinese restaurant process. So actually so let me actually explain the stick breaking process through this particular diagram. So now in this particular question, my k is still finite, but now I want to extend it to infinite dimensions. So how do I do that? And the motivation to introduce stick breaking process is basically to extend that finite mixture model to an infinite setting. And here is the process basically. So imagine you have a stick of a unit length. So the length of this stick is basically 1 unit. So you basically draw from a beta distribution, the beta one, and then you assign it to pi 1. So that's my first mixture. Now you take 1 minus beta 1, which is the remainder of the stick. So so basically you are cutting the stick, and so you break the stick at beta 1, and now I have 1 minus beta 1, which is left. Now again, I take a draw from that beta process and draw another beta variable beta 2, and beta 2 times 1 minus beta 1, which is basically the fraction of what is left, is pi 2. And then you can basically keep on doing this process again and again. So what you'll basically get here is pi 1, pi 2, pi 3. And if you do it infinite number of times, you'll have infinite pi. So this is one way you can easily extend your mixture model into basically what is called as Dirichlet process mixture model. So now G is essentially your, so earlier if G was finite, now your G is basically extended to infinite dimension. So okay, so this is the rest of the things are exactly the same. So your atoms are still dependent on that delta phi, which is drawn from the base distribution. Alpha naught influence is the height. You draw from this particular distribution, and then you fit a Gaussian around that particular distance. Everything is still the same. And then you might be thinking about, okay, this is all fine, but we wanted to do clustering. Where is the Chinese restaurant process, and how do we extend it? So all you have to do now is like integrate across G and G naught. So remember, like the theta I are your clusters, and xi are the number of persons sitting around that table. So this is a table, and xi you are getting the number of people. So this you are basically, so here are the flow of thoughts in this process. You started with a mixture model, which was finite dimension. And then you introduce something called as Dirichlet process, where you can basically extend the mixture model, finite mixture model to infinite setting. And then once I have the Dirichlet process mixture model, I'm marginalizing the probability distribution to get something called Chinese restaurant process, which we have already seen. You can have infinite number of tables, so you can actually learn infinite number of clusters. Okay. So now, so that was good, but there are a couple of more motivations. We want to keep going and think more about how can we, extend this to some richer models. So another motivation is, suppose like you have corpus of, you have access to data from different machine learning conferences, say NIPS, ICML, Sigmoid, and all these different conferences. And you kind of know that these different conferences are though different, but there is some underlying sharing going on. There are some common factors. So essentially, if I have access to all this data set, even though I have to treat them uniquely, they are their own data sources. They are of different quality, different people are probably there, but there is underlying theme that, okay, all of them talk about machine learning. So there must be some sharing which is going on. So can I extend the Dirichlet process, which we have heard, to this hierarchical setting where I have different number of corpus, but I still want to have that kind of a sharing. And this is the motivation for something called as hierarchical Dirichlet process. a naive attempt to solve this might be, okay, I have different corpuses, so let me run Chinese restaurant into each of them, or actually let me do something as simple as a likelihood estimation. But this will give you, one, this is kind of like a hacky approach, and two, like you will not get any sharing across different clusters. Actually, at least it's not guaranteed to get, there might be some luck factor which might, because of which you can get some sharing, but you are not explicitly modeling your parameters to be shared across different, clusters. Then MLE will also be noisy because, like, let's say NIPS will has a high rejection rate. So it's very selective. So probably you don't, versus some random conference XYZ, which is of machine learning, but they tend to accept all the paper you submit. So they'll have a lot of data. NIPS will have very less data. So you don't have a lot of data. So it will be a noisy estimate. So, and like I said, it's more of a hack than what you are trying to do. So you say, okay, you know what, let me introduce another parameter theta, which kind of influences this, the parameters to the model. So now I have introduced another hyperparameter theta, which kind of says that, okay, this is how all the parameters are shared. So maybe if I learn things in this particular fashion, I am explicitly saying that theta should come from some base distribution, and maybe I can influence, the end result. So let's see how that goes. And this essentially is called as the Dirichlet process admixture model. So it's basically the same thing, but if you notice from the Dirichlet process, all I have done is added one more plate, which basically means instead of 1G, I have GIs, one for each document. But this model fails very badly, and the reason for that is essentially your G0 is a continuous measure. For each document, I am drawing some distribution GI, which I am getting some atoms. And then, like, you run a Chinese restaurant process, you get some clusters for this document. For the next particular document, I again draw something from the G0. Since G0 is continuous, the probability that those two atoms will collide is almost zero. So if I get some atoms for G1 over here, probably for G2 I'll get over here. And if they are not colliding, these two documents will not share anything. So like the end clusters you will get will not share anything in common. So, and that's what we were trying to do. So this particular model will fail completely. At least whatever we were trying to achieve, you won't be able to achieve that, which was like the sharing of clusters across different corpus. So, okay, what do we do now? Like, so the issue was G0 is continuous measure. So maybe we can make G0 to be discrete and random, and you can almost say that this is almost cheating. If I know where my atoms which corresponds to the clustering, I don't need to do anything. I already know everything about the problem state. But like what we are saying is like G0 is discrete, but it's also random. So I know there are some finite discrete number of, so there are some discrete number of atoms, but I don't know where they are. So maybe that's what the Bayesian machinery is. So how do we solve that? So the answer is not to go frequentist, but actually to go more Bayesian. So, okay, so this is, now we introduce another parameter h, which is also called, like you can think of it as mother of all parameters. And then now we basically draw G0 from a Dirichlet process from h, and then each of the G, actually let me demonstrate it through this particular model. So now I have introduced another parameter h, which is a Dirichlet process. And now I draw G0 from that particular process. And basically now I am sampling from this. So now I'm not directly sampling from, or I'm not directly drawing from a continuous measure, but now I'm drawing from a discrete measure. And this will ensure that in different draws, there is some probabilities that this, clusters or this atoms will collide. And then basically now, and this is essentially what the equations are saying, that you draw from h, which has a hyperparameter gamma, and then like each of the GI is drawn from that base G0, and rest of the things are the same. And believe it or not, this also has a metaphor called Chinese restaurant franchise. So, and here is exactly the metaphor. So actually, to get from there to a clustering model, you basically have to integrate out all the G's in H. So if you integrate all the G's in H, then you get actually the Chinese restaurant franchise. And what does this metaphor actually mean? So basically, I have multiple Chinese restaurants, and then I have a global buffet line. Basically, everyone has a global menu. So the first person comes in, and then like they go to the global menu, pick up some dish, and come and place the dish on the table. Any other person who is coming to that particular restaurant and sitting in the same table, they will inherit that particular dish, so they'll eat whatever that first person has bought, or again, they are free to join any other table. But when the people are going and getting the dish, what they are also doing is let's say there is a tagger over there. So you are putting a cross over there that, okay, whenever you pick a dish, you put a cross next to the dish indicating that, I have picked up the dish. So how I decide I'll pick up a dish is basically dependent on how many eggs that particular dish has. So it's again like the same rich get richer model. So if there are more crosses next to a dish, the probability of that dish being picked is more. So basically, and that's how you essentially get sharing. A dish can be present in multiple different restaurants. And then what the dish actually represents is cluster. So when this dish, let's say some kind of like dumpling, I pick up a dumpling, you have a dumpling over here, here, here. So that's how you get a sharing. And it's actually exactly the same what we have described here. If I integrate all the G's and H's, you actually get this particular process. Okay, so let's quickly go through what we have gone through. So we basically introduced this particular field and then kind of worked through the theory, which was the motivation or like the prerequisites to understand Dirichlet process, and extended that to something called as hierarchical Dirichlet process. And there are actually a lot of metaphors. So all the clusters we have learned, though you can learn infinite clusters, but they are still flat. If you want to learn, let's say some kind of hierarchy, there is something called as nested Chinese process. Then in all this scheme, you can still extract features. So we are learning clusters, but we can also summarize the documents. But if you directly want to learn the features, you have something called as beta process, which is like the metaphor for that is Indian buffet process. And then like you have hierarchical beta process. So if you have to think about it, this is clusters, this is tight clusters, this is hierarchical clusters, this is extracting features, this is tying features together. And then you can also do non-parametric regression. I haven't talked about the inference techniques, but like those are, each of this can be go through. I'm sure in non-parametric Bayesian class, all of them are like lectures on their own. Okay, all this metaphors and all this stuff is really cool, but does this like learn something, or like how are the results? So let me quickly go through a demo. So this is actually a data set. You can get it from UCI repository. So basically what these are like the proposals submitted to NSF. So all these are abstracts basically. And then So basically we started with one cluster, and we'll run it through 1,000 iterations. So you can see like the number of iterations, like the number of clusters are not fixed, like they are growing with each of the iteration. So let's see how the results are actually for this. So 22 seems to be the appropriate number of clusters based on whatever the hyperparameters we had. And you can control this hyperparameters, and like you can control the number of clusters you want to see. So okay, so these are the results. So in the end, there are 23 topics which are learned. So the first cluster seems to be more about the I guess biomechanics and stuff like that. Then probably like these are about the solar cells and all this stuff. So you have volume, water, and all those. So I think like these are pretty good clusters. And remember, like the number of clusters is kind of like determined. We can have some influence on the number of clusters, which is basically your prior and how much you believe on your prior. But in the end, like these are adaptive depending on how your data is going. It'll automatically figure out the number of clusters in your data. Okay, so the title of my talk was like feature engineering is machine learning. And like, so why I want to stress on this is actually, I think what you do in the initial phase is very crucial. Like I have seen a lot of times when I am working that you do something beforehand and initially you don't even understand your data well. And like the choices you make beforehand kind of influences a lot of things. Like, so understanding your data well is really crucial, and like maybe the existing techniques will work well for most of the domains, but definitely like you want your models to do most of the heavy lifting, and you don't want to impose a lot of assumptions. So if I am doing clustering and I am using k-means, I don't want, without even knowing anything about my data and like this data set which is an infinite dimension or like a very high dimension, if I am working in parametric space, I don't even know about the data, like how, it just feels like how can you, setting some k beforehand is a very, very heavy assumption when we don't know about our data set. And deep learning is actually another example where you have rich models and you are doing feature extraction. We have seen so many instances where like we are under, like in deep learning, where, you know, what are the important edge which describes a cat, right? Like the famous Google example. But like those are all, I think those are all black box models. It's very hard to reason about them. Whereas like these particular models are probability distributions, and you can easily reason about like, okay, here is my probability data structure. And if I marginalize about across these parameters, then you can kind of like, these are easy to interpret. Whereas like, I think deep learning or neural nets in general tend to be more black box model. So yeah, I think, I can take the questions, but definitely like I'm also the student of this field. So a lot of these things like is influenced by the talks from like Michael Jordan, Yuvati. Then you have people like Zubin Garbani who are like doing research in this field. So definitely like if you are interested in these fields, you can find a lot of resources online. And like there are a bunch of very high quality material out there. And yeah, I can take some questions.
Any questions?
There are.
Sorry.
And there is one at the back.
One? No. Right behind the pillar.
Sorry if you answered this already, but is there somewhere that your slides are available?
I think we'll be posting it. I can work with Chester and basically, I'll basically make it available definitely. Yeah.
I had a question about, I guess, some of the challenges that come up using Bayesian techniques in production pipelines. Is there anything you can talk about that?
So, I guess like there are, I think, so there are a couple of areas where I think the Bayesian abstraction will not work very well, and maybe it's more about the traditionally how the field are level. So definitely something like A/B testing where you need statistical guarantees, like how confident you are. And I think like maybe there are some Bayesian interpretation to it, but definitely like I think basically like in frequentist domain, you are always thinking about what are the guarantees and that your model is correct. So anytime where you want those guarantees, I think frequentist approach work very well. But like in practical setting, I think the Bayesian approach, like it's very good to represent your uncertainty in your data. And general, like I kind of feel like the Bayesian tends to be, what's the word I'm looking for? They are more, they think they can model everything, whereas the frequentists are like a bit pessimist. Like I said, they want guarantees. So I think like it's more about the, I would say, culture thing or the background thing, like what your background is and like how you view your problem to be. I don't think there is any like problems. And so for example, something like GraphLab have libraries like belief propagation. I think now they are called DATO, but belief propagation and all that. So they are also like graphical models and you are inferencing on them, and I think they are robust enough. And so I think it's more about what you are comfortable working with.
Another question about Bayesian inference, just in general. Would it be fair to say that Bayesian inference has to have a good sampling of the entire space of possibilities, and that if you're looking for something like a law of nature, let's say if you were trying to learn the law of gravity, and you only measured it over a small sample or an insufficiently large sample size, you'd actually get it completely wrong.
Sure, yeah. And that's where like the priors come in, right? Like so priors, so like I said, like the Bayesians, like you say my data set is fixed, so if my sample is very small, then okay, I have fixed my problem size, but like all the uncertainty is represented in your parameters, which are actually influenced by priors. So if you are not very sure about your particular data set, then it's your priors how you can influence your posterior distribution basically. So that's where like the second part comes in. You have the likelihood, but you also have the prior part.
Hi, I'm just curious how you might be applying this to music, if you are.
So there are a couple of direct uses. So one direct use case is like we have a lot of, so one of the things we are interested in is like understanding our basically artists, and we have a lot of biography information across them. So a very direct use case is like, okay, I have some number of artists, and then like basically I want to cluster them and like try to figure out like, I don't know anything about them, but maybe like this is one approach that how we can extract the group different artists together underlying like some, so like, but like I also want to say like though we have built this particular abstraction, but like we haven't deployed it, but that's mainly because of the internal data quality issues, which is like I have all this raw text data, but now the second part of it is like I have this textual data, but I want to associate it with some audio ID inside, and that's a very, it is not as easy as we would like to be. And then definitely, if you think about it, you can, it's not very directly obvious, but you can actually extend it in recommendation systems as well, where your table essentially kind of represents what are all the users and items which are grouped together, and maybe that's a good way to recommend them. So it's not very, so though like the underlying application I've kind of driven through topic modeling, because that's how like the normal field, like this particular field is introduced, but you can definitely think like your clusters are actually some higher level concepts which tie your user and items together. You can use that. So, but those are like some of the ways we are thinking about like how maybe in recommendation we can also use this. Yeah. Actually, yeah.
Kind of concentrated on unsupervised learning kind of things. Can you apply it to supervised? And I guess I have trouble seeing how you solve the explaining away problem with that interchangeability, because if you have a directed graph, I don't think the joint probability, you can't switch them all of a sudden.
So let me actually address the first question. So in supervised learning, where is it? So you can actually do non-parametric regression. So all this, so think of, so Dirichlet process is basically one of the many processes. It's like a function. If your process, if your measure is, if what you have is a measure, if your probability distribution is a measure, you get a Dirichlet process and you get something like densities and stuff. If Gaussian processes, if your probability distribution is more like a function. So if you are trying to approximation a function, so if let's say I have y equal to g of x, where now g is the same stochastic process, but now it represents a function. So you can extend it into the regression case as well, but now it's basically non-parametric in that sense. And I think like the other question you asked was basically about exchangeability, I think, or which one?
It's not in these.
Oh, I don't have it. So
if I had buzzes, like classic thing, grass is wet, it could be, or like, and evidence for way the other.
Sure, yeah. So not everything in this graphical model are random variables, but like they are also sequence of random variables. So G is not just a random variable, but I have infinite many random variables. So so basically what we are doing in this particular scheme is I don't think we are like reversing it, but all we are doing is like I have some infinite number of random sequences of I have infinite number of random variables, and then how I'm just drawing something from that particular sequence. And I can actually, and what Definity theorem tells me is basically that it guarantees that if the sequence is, if I have an infinite sequence, I have some G through which I can, basically if you think over here, like because of Definity theorem, now I have infinite number, all these thetas are being extracted in independent manner. So I have like all these documents. So all of these G's are kind of independent, and they come from Definity theorem. So a lot of this is, so basically, though I haven't gone in depth through in explaining that, but most of the things we are doing is basically from this one slide is everything, all rest of the stuff like the beta process and all those stuff are just a derivation of that, like how we are applying this particular fundamental theorem. But where this particular theorem was introduced, like they talk about a lot of guarantees and like why we are doing this and why it makes sense. So.
Any other questions? Okay, well, let's go ahead and thank our speaker. We do have another meetup. I think it's next week, and our speaker will be from Yelp, and look at the website for more information. And thanks for coming.